first installment of our Radar Scope webinar series, where we talk about the basics today. But first, let me introduce you to Mike Wolfenbarg, who is the guru of Radar Scope.
Good afternoon or morning, everyone, and welcome to the first installment in our Radar Scope Lunch and Learn series. I'm Mike Wolfenbarger, and I'll be your host. I'd like to introduce Daphne Thompson, who heads up our meteorological outreach. Daphne will be presenting today's Radar Scope topic, and at the end, I will show you the recent integration of Radar Scope into our cloud-based enterprise platform, and touch on a few of the many benefits our clients receive with its actionable weather intelligence. Before I turn this over to Daphne, I'd like to briefly tell you about Weather Decision Technologies. You're with us today because you use Radar Scope, which is one of the top 3 mobile weather apps available on the mobile market today, with more than 300,000 users globally. We're excited that 500 of you could join us today. Another fact about WDT is that we hold and license 58 patents related to weather detection technologies. I can tell you we're not even close to being done leading that charge. You, as customers of WDT, are the reason we keep innovating. I'll now turn this over to Daphne. She holds a degree in meteorology from the University of Oklahoma and brings to WDT a deep pool of knowledge. Her previous experience includes working at the National Weather Center, the Norman Emergency Management Office, and the National Weather Service. And Daphne serves in a meteorological capacity for WDT. Daphne, you have the audience.
Hi, everyone. So today we're going to be talking about a lot of basics on radar. You can see our topics for the day will be basics on how radar works, data varies from storms at different distances, and frequent updates and faster data. So let's get started with the basics. So a lot of people have seen radars like this, and they think they're giant golf balls. Instead, what we are looking at is a fiberglass radome. Inside that is the weather radar. The pattern of the radar was designed to prevent the radar beam from being blocked. It also protects the radar from the elements. One thing to be aware of is that radar beams do not look like lightsabers because the beam is not uniform. Instead, a radar beam more resembles a flashlight. As the beam gets further and further away, it becomes wider and higher. A radar beam rotates within the radome, and it elevates when it's looking for weather. These are called tilts. It is important to note that radars do not look at ground level. They're actually looking higher into the storms. The National Weather Service has radars located all over the United States. These are referred to as WSR 88Ds, which stands for Weather Surveillance Radar, 88 for the year it was developed, and D for Doppler. There are a total of 164 of these sites in the United States. This includes Alaska, Hawaii, Guam, and Puerto Rico. There are also 45 terminal Doppler weather radars, also known as TDWRs. They're located at airports. They are used to detect weather that could affect aircraft, such as wind shear and precipitation. Placed in thunderstorm-prone areas, they assist air traffic controllers by producing high-resolution data. When looking at the radars displayed on Radar Scope, you can tell the difference by viewing the name of the radar. A WSR 88D identifier will start with a K, while a TDWR identifier starts with a T. Let's compare an image from a WSR 88D to that of a TDWR. The radars I'm using are very close to each other, and the images were taken at nearly the same time. Here you can see rain and small thunderstorms around Wichita, Kansas. Note that in the lower left corner it says the beam elevation is 0.5 degrees. Now let's see what a TDWR image looks like. They use a different color table, so that's one difference. The beam is also looking lower than it is on the 88D. Again, look at the lower left corner and you can see the elevation here is 0.2 degrees. Although the very light rain showers do not show up, the heavier rain is very visible. So let's check that out. We can see that by going back and forth. The heavier rain still remains there. An air traffic controller would probably zoom in closer than I am in order to see the higher resolution data in more detail. Another difference between these two radars is the distance that the beam extends to gather data. The beam range on a WSR-88D is about 143 miles from the side of the radar. Here you can see the range extends southward towards Oklahoma City and north past Topeka. Because this TDWR has a thinner beam, it is able to see in higher resolution. But that means the beam is not able to go as far. The range is only about 56 miles from the side of the radar. That is why it's used for airports. You can give much better details for storms nearby when planes are landing. All right, our next section is about how data varies. Let's look at some more radar scope images. Here we see some storms located near Frederick, Oklahoma, and extending further north. When a radar is far away from the storms, the beam has further to go. This means the beam is pretty wide by the time it gets to the storm. It also means that the beam has broadened like a flashlight beam does. So far, a storm far away from the beam is actually looking very high up into the storm. Weather occurring at low levels may get to you earlier than you thought, so make sure you know what you're looking at before making any major decisions based on radar. Using the radar scope distance tool, we can find out exactly how far we are looking and how high up the beam is when it gets to the storm. In this case, the Frederick storm is over 125 miles away from the radar located near Oklahoma City. This causes the beam to be nearly 14,000 feet up in the storm. Let's look at that exact same storm, but this time we're using a radar that is nearby. When storms are closer to the radar, the beam doesn't need to go as far. This means the beam does not widen much. It also means that because the beam isn't as high into the storm, you will get a more accurate image of what is occurring. Weather may still reach you sooner than expected since the radar is not looking at ground level. Let's use the distance tool again. The closer radar is actually very near to the storm approaching Frederick. Now the radar is less than 5 miles away from the storm, causing the beam height to only be 200 feet up. That's much better than the last image where the beam was close to 14,000 feet high. Here we're looking at the same images again. On the left, the radar near Oklahoma City, depicted as a star, was quite far away from the storms. On the right, again depicted by a star, we see the Frederick radar, which was very close to the storm. If we zoom in on the storm near the town of Frederick, you can see how blocky the image is. Remember, the radar beam is pretty wide at this point and high up into the storm. Now let's zoom in using the closer radar. This image is much more detailed. The size of the storm is also more accurate. Comparing the two, you can see why you would want to view storms with the closest radar available. If you turn on the Storm Track tool, you can also learn more about the path of the storm. Each of the tick marks signifies where the storm will be in 15-minute periods. This basically uses a mathematical algorithm or formula to try and forecast where the storm will be, depending on how fast and what direction it is currently moving. Over time, this can also vary if the storm changes speed or direction. When there are multiple storms in the area, each will be labeled and have their own paths displayed. All right, now we're going to talk about faster data. Radars are always on, night or day, storms or clear skies. Here we have a loop of data. This is on a normal day with rain showers. You can see the showers are moving to the northeast. I'm going to play it again. This time, watch the clock. You can see the images are coming in about every 4 to 5 minutes. So this loop is about an hour and 20 minutes long. Now let's watch a loop of a severe storm that produced a tornado. Let's play that once more. And again, look at the clock. On a severe weather day, the radars spin faster and gather data images every 1 to 2 minutes. This loop is about 30 minutes long. Because of that, the storm appears more ominous. It's always a good idea to check how fast images are coming in. It can make a big difference on when that storm gets to you. Well, that concludes lesson 1, but don't forget to come back next week for the next session. Now I'm going to turn this over to Marcus to close out today's presentation.
Thank you, Daphne, for sharing your expertise and knowledge with us today. But we're not done just yet. We're still talking about RadarScope, and I'm really excited to tell you about the recent Weather Ops update that now includes RadarScope. With this recent integration of RadarScope into our enterprise platform, our clients are enjoying the benefits of high-resolution radar data that you've all enjoyed. But combined with other incredible tools that were already part of Weather Ops, it's like RadarScope on steroids. Now, with this week being Business Continuity Week, this portion of today's presentation is for those of you that are interested in how RadarScope can help your organization minimize risk, protect your human assets, and your bottom line. So what is Weather Ops? It's a cloud-based meteorological decision support portal that provides information to support critical decisions as they relate to disruptive or dangerous weather. Our Weather Ops solution bridges information and timing gaps by providing the same critical information regardless of geographical location to key personnel using the best methods of delivery, such as email, text messaging, or mobile device push. There's no more coming back to the table and discuss the differing bits of information everyone receives separately and then create a plan. Our team taps you on the shoulder well in advance. And when we do alert you, your key team members can receive the same alerts, allowing them to instantly put plans into action. This directly impacts the bottom line in a very positive way. Here's how it all works. We call this our forecast funnel, and it's the typical flow for disseminating forecast and threat information. It starts with our daily planner. These are issued once daily at 6 a.m. by our team of forecasters, and it's color-coded to allow for easy identification of the types of threats you choose for your assets. This planner is completely customizable in terms of the criteria that is impactful to your organization. The hazardous weather outlook is part of the preemptive tax on the shoulder. That hazardous weather outlook is also issued daily by our team and is in-depth analysis of potential hazardous weather that could affect your business. Key forecast drivers and forecast justifications, probability-driven assessments for each key weather parameters, and regional discussions can be sent as needed or required during periods of hazardous or inclement weather. Like the daily planner, our weather checks is still that same color-coded, easy reference identification of those threats periods to get you ahead of making critical decisions related to adverse weather. Threats that were identified in advance using the daily planner are broken down in the weather checks as the events draw closer. Weather checks are useful in timing guidance by identifying key hazardous periods over the next 2 days in smaller time blocks. Storm advisories and alerts are short-fuse, event-driven alerts. These alerts will provide you with details on exact timing and threat type. There's over 20 categories that we alert for, primarily severe storms, tornadoes, heavy rain, high winds. And with this platform, you stay connected and informed no matter where you are. Combined with our mobile decision support companion, you have instant access to radar, daily planners, weather checks, and alerts. You'll never wonder again if it's time to take action. Now, I'm sure each of you have something to take away from today's session. Maybe you learned something new, or you were able to confirm something that you were already thinking. I hope that you feel more confident in understanding radar and how it works, and using RadarScope more and more. If you currently use RadarScope to help your company react to weather threats, give me a call and let's discover how weather ops can help you better prepare and react. And with that, this concludes today's session. Thank you all for joining, and have a great rest of your day.
Good afternoon or morning, everyone, and welcome to the second installment of our Radar Scope Lunch and Learn. My name is Marcus, and I'll be your moderator for today. If you have any questions during today's presentation, you can write your question in the chat window. And also be sure, if you tweet or post on Facebook about Radar Scope, to use our hashtag #RSWX16. I'd like to introduce Daphne Thompson, who leads up our meteorological outreach, and Daphne will be presenting today's Radar Scope topic. And at the end of today's presentation, I'm going to tell you a little bit about Skywise, Weather as a Service. Remember, Radar Scope is one of the top 3 mobile weather apps available on the mobile market today, with more than 300,000 users globally. Another fact about WDT is that we hold and license 58 patents related to weather detection technologies. But what you don't know is that many sources you currently go to for your weather news and information get some or all of its data from WDT. I'd like to now turn this over to Daphne. She holds a degree in meteorology from the University of Oklahoma and brings to WDT a deep pool of knowledge. Her previous experience includes working at the National Weather Center, the Norman Emergency Management Office, and the National Weather Service. Daphne serves in a meteorological outreach capacity for WDT. And with that, Daphne, you now have the audience.
Welcome, everyone. Last week, we discussed some basics on weather radars. We learned that the covering is called a radome, and that the radar is contained within it. We also talked about how data can vary depending on the distance it is from the radar. Storms farther away can end up having the beam height thousands of feet up in the atmosphere, while storms closer to the radar give a more accurate representation of the storm. Here we have a storm near Frederick that is far away from the radar near Oklahoma City. The image is very blocky. And here we see the same storm with the radar much closer. The image is much clearer and more accurate. Today, we are focusing on reflectivity data from Radar Scope. We will be covering the following topics in this webinar. First off, color tables and rainfall. Then we'll have the difference between hail, rain, and other things. And finally, I'll talk about the difference between base reflectivity and super res reflectivity. So first off is color tables and rainfall. Whether you want to check out the rain or wanting to view a supercell thunderstorm producing a hook echo, reflectivity radar can help. Reflectivity is a radar product that displays the amount of power returned to the radar after it is reflected off particles in the atmosphere. It is measured in decibels, which is abbreviated as dBz. So what does that really mean? Well, when the radar sends out a beam, some of the energy from the beam is reflected back to the radar. Small objects, like tiny raindrops and bugs, will send back a smaller amount of energy. Larger objects, like big hail, will send back more energy. The energy that returns is then assigned certain colors. Here is a very colorful reflectivity image from a severe thunderstorm in South Texas. Yellow signifies moderate rain. The orange area will be experiencing heavy rain. Areas in red have very heavy rain and probably some small hail, while pink areas have intense rain and possibly large hail. It is important to note that these values usually change when viewing a hurricane. So the radar sends out a signal or energy while it rotates and scans the atmosphere. Then it listens for the energy reflected back. It also elevates the beam during each scan. Each elevation change is referred to as a tilt. Radar Scope allows us to view 4 different tilts of radar data. Here we have a severe thunderstorm west of Austin. Let's focus on the heaviest rain or hail in the warning. I will keep the distance from the radar exactly the same and only change the tilt level. One thing to notice is that not all the tilts come in at the same time, but all of these images were captured within a few minutes of each other. Tilt 1 shows us the radar at this distance is 6,300 feet high. Tilt 2 is at 8,400 feet high. Tilt 3 we find at 11,100 feet up. And Tilt 4 has the radar gathering data at 14,600 feet. This can be useful in finding out if a storm is only intense in lower scans or if that intensity is found throughout the storm. As the radar sends out its signal, the beam travels out and returns energy along the way until it gets to this max distance. If a beam is going through rain, it bounces off the raindrops and leaves less energy to travel to more distant storms. So sometimes a storm further away may appear weaker than it really is because another storm closer to the radar has not allowed more energy to get to it. You've probably noticed that storms far away from the radar and at higher tilts can give a blocky appearance. These blocks are more formally known as pixels or gates. It's a bit reminiscent of an 8-bit video game. Since the radar spreads with distance, the pixel size changes as the radar beam gets further away from the radar. You can see the pixels along the beam here. This is called a radial. It's like the spokes on a bicycle wheel. There are multiple radials extending from the radar in this rainstorm. By the way, these pixels aren't flat. They are three-dimensional boxes. If I measure the size of a pixel at the max distance from the radar, you can see that, in this case, it is about 2 miles wide. Now let's look closer to the radar and measure the same distance. Now about 40 pixels fit in the same width. Sometimes people will smooth the radar data so that you can't see the individual pixels. Although it may look pretty, it is not accurate, especially when they overlay it on a map and try to make you believe they can see exactly what is going on at an intersection in your town. In reality, the radar pixel may be the size of your entire neighborhood. Let's return for a moment to our radar sending out a signal and receiving the reflected energy. Remember, the data returning will be displayed as pixels and colored according to the decibel measurement. The three-dimensional pixels can contain raindrops, hail, bugs, smoke, and other non-weather items. Here we have two cubes that represent pixels. The one on the left has large raindrops, and the one on the right has lots and lots of small raindrops. When the radar beam bounces off these drops, it will return the same decibel value. That's because a regular weather radar is not able to differentiate between the two. While the reflectivity values are the same, the rainfall rates will differ substantially. Let's move on to hail, or rain, or something else. Have you ever heard the TV meteorologist say that there was going to be nickel-sized hail where you live, and instead you ended up with giant raindrops? Just as the radar is not able to tell the difference between large raindrops and lots of tiny raindrops, it can also have problems telling the difference between large raindrops and hail. So while the reflectivity values may be the same, what you get when the storm arrives may be different. However, sometimes radar images can show that hail is in the storm. These are called hail spikes, or three-body scatter spikes. If you ever see this, there is a good chance that there is very large hail within the storms. This is a false signal or echo. There actually isn't any rain occurring there. What happens is that the beam leaves the radar, it hits the large hail and bounces to the wet ground. Then it bounces back to the hail before finally returning to the radar. This confuses the radar, making it believe that there is more rain beyond the area of hail. When you view the radar data afterwards, the hail spike appears. There are many things we can see on reflectivity data. On the left is a thin line front moving to the southeast. Many times these will have bugs that get caught in the wind change, and the radar is reflecting off of them instead of rain. The same thing happens in the outflow of thunderstorms, seen in the middle image. The picture on the right is displaying a squall line with a trailing rain curtain. Let's look at some more radar scope reflectivity images. Here on the left, we see some rain bands on the East Coast associated with Hurricane Sandy. The middle image is that of a blizzard in the Denver area. What do you think we are looking at on the right? If you guessed some sort of precipitation, you'd be wrong. This was from a clear summer day. What you're actually viewing is a horde of grasshoppers. Park rangers reported this swarm. Otherwise, it would have been very hard to know what was going on. Sometimes it's hard to know what you're looking at without additional information. Here, the image on the left with the bright pink areas isn't heavy rain. Those are wind farms. Tall buildings and towers near a radar can block the beam and give false signals. Meteorologists aren't the only people who look at radar. Ornithologists have been known to view radar to keep track of birds and bats. We see bats leaving their caves in the center image. You can also use radar to see smoke when large fires happen, as seen on the right. I'm going to show you a few videos now. If you have a weak connection, they may not show properly. Remember, this webinar is being recorded so that you can go back and view it again later. So what I really enjoy is viewing loops of interesting storm features. On the left, check out the curlicue that goes through Frederick. Let's watch that again. The middle video shows us a feature called a bookend vortex. The top of the squall line begins to rotate inwards. We'll take another look at that. And of course, loops of reflectivity are also great for picking out hook echoes in supercells. This caused a damaging tornado near Tulsa. My final section is about base reflectivity and super-res reflectivity. What is the difference between base reflectivity and super-res reflectivity? Let's look at the same storm taken at the same time. Both images use 256 colors to display the data. On the left is base reflectivity, and on the right is super-res reflectivity. If you recall from earlier, the pixels along a beam are called radials. In the base reflectivity, the radial is using wider pixels. But super-res shows the full resolution of the WSR-88D. You can see the pixels are about half the size as on base reflectivity, so the image ends up being higher resolution and able to show more atmospheric details. If you want the most detailed image on radar scope, make sure you are selecting the super-res reflectivity option. Let's review some of what we learned today. Reflectivity displays the amount of power returned when the beam reflects off particles in the atmosphere, such as raindrops. As a radar rotates and elevates, this gives us various tilts. Radar scope lets you look at data. When looking at storms, the line of pixels is called the radial. Pixels get wider as they get further away from the radar. Be careful of places showing very smooth data because it is giving you a false view of the storm. The super-res reflectivity data found in radar scope is true high-resolution radar data and is not smooth. Finally, reflectivity data is a great way of viewing storms, but it also shows non-weather phenomena like bugs, bats, and smoke. Next week, we will be talking about velocity data. Right now, though, I'm going to turn this presentation back over to Marcus.
Thank you, Daphne, for sharing your knowledge and expertise with us again today. But we're not done just yet. I'm really excited to tell you about Skywise, a premium weather data for developers that might be interested in including premium data into their own applications. So as I said, Skywise is premium weather content and analytics that you can utilize for any size project. With Skywise, you can access an enormous amount of value-added weather data and analytics never before available outside of WDT. Skywise will empower web, mobile, GIS, software as a service, and common operating picture developers, as well as data scientists, the ability to tap into a substantial catalog of weather analytics and information. Excuse me. The Skywise Current and Forecast API provides access to current weather conditions for any location across the world, as well as hourly and daily forecasts for the next 10 days, utilizing WDT's proprietary weather prediction solutions for use in any application. Add WDT's conditions and forecast data to your mobile application, and WDT's feeds can drop right into any iOS or Android implementation. And because it's a library, it's easily added to your apps and offers over 24,000 current weather observations. This feed is additive, meaning you can bring additional content from other sources if you would like to combine sources within your apps that you utilize with our stuff. Now, WDT provides a turnkey interactive weather map solution for mobile app developers. Skywise tiles drop right into any MapKit implementation with ease. And again, because it's a library, it's easy to add to your apps, and there's no source code to be concerned with. Skywise tiles are also additive, meaning you can bring additional map layers from other sources that you can combine with your own. We can serve you all types of different data sets: marine and wave, aviation, radar and satellite, point and contour, along with forecast models. We can also provide you with lightning data. With our Skywise platform, you'll have access to the most complete lightning data available. WDT Skywise is an authorized distributor of both the Worldwide Lightning Location Network and Earth Network's Total Lightning Network data. The power of these global systems are immense, and immediate value can be added to your project. We make it really easy to integrate both LDM and HTTP delivery types of this data. Now let's take a look at a couple of popular apps available in the mobile marketplace that uses WDT Skywise data. First is the NOAA Weather Radar by Avalon. NOAA Weather Radar is a powerful yet easy to use weather station right on your device. Simple and stylish, but technologically advanced, OneWeather offers an alternative to cookie-cutter type apps. A full suite of accurate, up-to-the-minute weather tools can keep you informed. And again, utilizing WDT's data. On the ground and in the air, pilots worldwide depend on ForeFlight Mobile for flight planning, charts, weather, airport information, document management, synthetic vision, and much, much more. And in the aviation environment, pilots using ForeFlight depend on WDT for their flight planning and en route weather. Scripps Storm Shield, which is distributed across their network areas, utilize our data so their customers can get severe weather alerts for exact locations, again, on their iPhone or Android device. All of the weather data that you would ever need, you can get directly from WDT. Don't get your weather data feed from a bargain basement or even free sources. has guaranteed uptime and extremely fast delivery. As you've just seen, many sources of weather data that you could be receiving today might just come from WDT. So get in touch with me by calling the number on the screen or send me an email and learn more about what types of data we can provide you for your own groundbreaking applications. And that concludes today's webinar presentation. I'd like to thank you all for attending and have a great rest of your day.
Our Scope Lunch and Learn series. My name is Marcus, and I'll be your moderator today. I'd like to again introduce Daphne Thompson, who heads up our meteorological outreach. Daphne will be presenting today's radar scope velocity topic. And at the end, I'm going to show you our cloud-based enterprise platform that includes radar scope and touch on a few of the many benefits our clients receive with that actionable and weather intelligence. But before I turn this over to Daphne, for those of you joining for the first time, I'd like to briefly tell you a couple of facts about weather decision technologies. You're likely with us today because you currently use Radar Scope, which is one of the top 3 mobile apps available in the mobile market today, with more than 300,000 users globally. And we're excited that 500 of you could join us today. Another fact about WDT is that we hold and license 58 patents related to weather detection technologies. And I can tell you that we're not even close to being done leading that charge. And you, as a customer of WDT, are the reason we keep innovating. I'd like to now turn this over to Daphne. She holds a degree in meteorology from the University of Oklahoma and brings to WDT a deep pool of knowledge. Her previous experience includes working at the National Weather Center, the Norman Emergency Management Office, and the National Weather Service. Daphne serves in a meteorological outreach capacity for WDT. Daphne, you now have the audience.
Last week we learned about reflectivity. When the radar sends out a beam, some energy from the beam is reflected back to the radar. Small objects like tiny raindrops and bugs will send back a smaller amount of energy. Large objects like big hail will send back more energy. We also talked about how pixels close to the radar are smaller than those far away. By measuring the size of a pixel at the max distance from the radar and comparing it to the size of pixels closer, you can see that more pixels fit into the same width. Remember, smooth data may look pretty, but it is not as accurate. When overlaid on a map, the radar pixel may be the size of your entire neighborhood. Today we're focusing on velocity data from radar scopes, and we'll be covering the following topics in this webinar. What the green and red colors tell us, is it a tornado? And then we'll also talk about base velocity versus super red velocity. First off, let's learn about what those red and green colors are telling us. When viewing the velocity product on radar, it is important to understand what you're looking at. It is a radar product that displays the average wind speed of particles that are detected by the radar. Notice I said particles and not precipitation. That's because it could also be able to see non-weather items like bats and bugs, and sometimes debris if a tornado is occurring. It is measured in knots or miles per hour. The Doppler effect is the change in the frequency of a wave for an observer moving relative to its source. What does that really mean? You've all heard the train blowing its whistle as it passes you by. When the train is approaching, the pitch of the whistle is higher, but as it passes, the pitch becomes lower. That is due to the frequency of the sound waves. They are closer together when approaching and further apart when departing. Let's hear an example. A similar effect happens with Doppler weather radar. I've replaced the person with a radar and the train with a storm. When a radar sends out energy and hits particles in the storm, it checks the wavelength to see if the storm is moving and the direction of that movement. Storms moving towards the radar increase the frequency of energy returned to the radar. When a storm is moving away, the frequency of the wavelength decreases. This change is also known as phase shift. Doppler radar is also known as NEXRAD, standing for Next Generation Weather Radar. And you've probably heard it called the WSR-88D, which stands for Weather Surveillance Radar, 88 for the year it was developed, and D for Doppler. Created in Norman, Oklahoma by the National Severe Storms Lab, the first prototype was installed in 1990. By 1997, all 160 network radars had been installed. They are operated and maintained by the National Weather Service. Prior to the advent of Doppler radars, only reflectivity was able to be measured. Doppler radar made it possible to also measure the speed of particles. Velocity data on Doppler radars is usually displayed in shades of red and green. The red shades may include pinks and peaches, and the green shades may include some blues. Green colors tell us that those particles are moving toward the radar. The red color signifies particles moving away from the radar. Here is a velocity image with the red and green and even some blue pixels that are very close to each other. The radar is located in the lower right of this image and not visible on screen. Remember, the red pixels are moving away from the radar, which is outbound, and the green pixels are moving towards the radar, which is inbound. When you see a tight area with the red and green areas like this, it's sometimes called a velocity couplet, it shows us the storm is rotating. We call this a tornado vortex signature. It does not necessarily mean that a tornado is happening, because radars do not look at ground level. But the storm is rotating fast enough to produce one. We can use the inspector tool in radar scope to actually measure the wind speeds of velocity data. We are still looking at the velocity couplet in this TVS. When I use the inspector tool, it will show up right in the center of my image. This means I need to shift my image in order to measure the pixels, also known as gates. The inbound velocity shows a negative speed of 71.6 miles per hour. Measuring the outbound velocity gives me a positive 48.1 miles an hour. When you add these two numbers together, you get the gate-to-gate shear for this TVS. The larger the number, the stronger the rotation. We've seen this image before, but let's review it again. Radars send out a signal or energy while rotating and scanning the atmosphere. They listen for that energy reflected back. The beam elevates during each scan, and each elevation change is referred to as a tilt. Radar scope allows us to view 4 different tilts of radar data. We are able to look at tilt and reflectivity and velocity data. Here we have a tornado warning in northern Oklahoma. We'll focus on the tornado vortex signature, or TVS, within the white circle. I'll keep the distance from the radar exactly the same and only change the tilt level. All these images were captured within a few minutes of each other. Tilt 1 shows the radar at this distance is about 6,300 feet high. At Tilt 2, we're looking 8,400 feet high. Tilt 3, we find up at 11,200 feet. And here at Tilt 4, the radar is gathering data at about 14,700 feet. If you notice, the TVS was visible at each tilt. This is a good way to know that rotation is occurring throughout the storm, leading to a radar-indicated tornado warning. The National Severe Storms Lab developed the tornado detection algorithm. Doppler radar uses this set of equations to detect rotation in thunderstorms. The National Weather Service will issue a radar-indicated tornado warning when the algorithm determines that rotation is strong enough to produce a tornado. This does not mean the tornado is on the ground, just that the storm is rotating fast enough to produce one. If you've ever looked at your radar scope velocity menu, you've seen super res velocity, base velocity, and this product named storm relative mean velocity. But what is this? Well, storm relative mean velocity is basically base velocity with the average storm motion subtracted out. Here we have base velocity on the left and storm relative mean velocity on the right. When storms are moving quickly, the motion can mask rotation in the storm. If we remove the storm motion, it gives us data as if the storm was stationary. Looking at these two images, you can see a velocity couplet on the left, but it doesn't show up well on the right. However, If we look at the interesting area near the bottom of this image, we can see the velocity couplet becomes much more apparent. Using this product can sometimes make it easier to spot velocity couplets that are indicative of rotation. So let's look at a few more velocity images in radar scope. Did you see all that purple coloring? What has happened is that the radar has sent out a beam of energy and listened for it to return. But the energy keeps on going and doesn't return what it's expected. So there's no return signal. So the radar just keeps on spinning, and eventually it gets back to that spot where it didn't hear anything back the first time. However, this time it does get a signal. The radar doesn't realize the signal came from earlier and assumes it is current. It then plots that signal that was late over more current data. Basically, the radar is confused and showing us bad data. We call this range folding. Range folding happens when the reflected energy from the radar that traveled into a region was unable to make it back before the next signal was emitted. The energy arrived late and is called a second trip echo. This confused the radar, and so that data is considered bad and now shows up as purple. Our next section is called Is It a Tornado? And we will be looking at velocity images and trying to figure out what we are seeing. Can you find the button with the green hand on your GoToMeeting control panel? I'm going to ask you some questions about velocity data. And if you think you know the answer, raise your hand. All right, so here are two images of very distinct gate-to-gate shear areas. The image on the left has the radar located to the bottom right, while the image on the right has the radar located near the top right. How do we draw our arrows to know more about what we are seeing? The couplets here show areas that are definitely rotating and would be considered tornado vortex signatures. The majority of tornadoes in the United States rotate cyclonically or counterclockwise, as we can see here. Remember, a TVS doesn't mean a tornado is on the ground because visual confirmation is still needed. In this image, the radar is located at the top left. So what do you think we're seeing here? I'm going to draw our arrows. Again, we have an area of rotation. But look at the scale compared to the size of the coastline at the top left. We're not observing a huge tornado over the Gulf of Mexico. We are actually looking at a mesocyclone. A mesocyclone is an area where a large portion of the storm is rotating, but is not tight enough rotation to form a tornado. Supercell thunderstorms rotate and have mesocyclones that can sometimes lead to a tornado, but it does not mean a tornado is occurring. Well, this image is a bit different. Take a look at it for a moment and try to figure out what's going on. The blue hashed circle is where the radar is located in this case. Sometimes you need more data. Here, the reflectivity image gives us a better idea as to what we are viewing. This is a gust front. It's just past the radar site. So people living southeast of the radar, it is about to get really windy for them. This one's a bit harder. Look and see if you can find the color discrepancy in the velocity image here. The radar is located on the left near the center. Do you see it? This is outflow. You can make out the thin line on the reflectivity image. And here it is on the velocity image. Outflow will cause a wind shift and temperature drop for those west of the storms. Well, what is this? Are we looking at some sort of Christmas-colored donut? The radar is located on the right. Now, let me give you a hint. This is near Austin, Texas. Is that helping any? Well, let's view the associated reflectivity image. Have you figured it out yet? What we are looking at is bats leaving their cave, and they're flying out in all directions. Want to test your new skills again? What are we viewing at this time? The wind speed values in the center of it have exceeded our normal greens and gone over into the blues. Does the reflectivity image help you out? This is a cluster of thunderstorms producing strong winds. You can see they are blowing towards the radar, which is located at the top and center. Here's one last test case for you. I'm going to show you a video. Remember, if you have a slow connection, the video may not play well for you. But this presentation is being recorded and you can view it later. Ignore that purple area of bad range folded data, but keep your eye on the red outlined polygons, which show tornado warnings. Did you catch it? Here, let me play that again. There were actually 2 tornado vortex signatures here. Remember, the radar doesn't look at ground level, so we don't know for sure if a tornado is occurring unless we have visual confirmation, which in this case we did. One of our employees captured this photo of twin tornadoes near Dodge City, Kansas just last week. So my final section is about base velocity and super res velocity. Let's talk about what those are. So what's the difference between base velocity and super res velocity? Well, let's look at a tornado warning where both images were taken at the same time. The same color table is being used. On the left is base velocity, and on the right is super res velocity. If you recall the last lesson, the pixels along a beam are called radials. In base velocity, the radial has wider pixels. But super res velocity shows the full resolution of the WSR-88D. You can see the pixels are about half the size as on the base velocity image. So the image ends up being higher resolution and able to show you more details. If you want the most detailed velocity image on radar scope, you need to make sure you are selecting the super res option. All right, so let's review some of what we learned today. First off, velocity is a radar product that displays the average wind speed of particles detected. It is measured either in miles per hour or knots. And the first Doppler radar prototype was installed in 1990 here in Norman, Oklahoma. Before Doppler radars, only reflectivity was able to be measured. Doppler radar made it possible to also measure the speed of particles. Velocity data is usually displayed in shades of red and green. Green colors tell us that those particles are moving toward the radar. The red colors signify particles moving away from the radar. Red and green pixels that are close to each other can signify rotation in the storm. We call this a tornado vortex signature, or TVS. You can use the radar scope inspector tool to check wind speeds. If you add those wind speeds together, it can give you an idea as to how strong the rotation is in the storm. The color here shows an area of rotation that would be considered a tornado vortex signature. The majority of tornadoes in the United States rotate cyclonically, or counterclockwise, just like this one is. A TVS doesn't mean a tornado is on the ground because visual confirmation is still needed. And while many of us only turn to velocity products to look for a TVS in a storm, you can actually view many different types of weather phenomena using velocity data. All right, well, I hope each of you has learned something today. Next week, we'll be talking about the benefits of Radar Scope Pro. But for right now, I'm going to turn this presentation back over to Marcus.
Thank you, Daphne, for sharing that knowledge and expertise with us again today. But before I tell you about weather ops, I want to announce that the Radar Scope Shop is now open. Show the world your superpowers and let them know that you have the ability to see into the storms too with Radar Scope. And you can access that on the web at radarscope.io/shop. Now let's talk a little bit about weather ops. This part of our presentation is for those of you that are involved with weather monitoring for your companies, sporting events, outdoor festivals, concerts, anything that has to do with needing to know weather. Now, with the recent integration of RadarScope into this enterprise platform, our clients are enjoying the benefits of high-resolution radar data that you've all enjoyed, but combined with other incredible tools that were part of Weather Ops. So what is Weather Ops? It's a cloud-based meteorological decision support portal that provides information support to critical decisions related to disruptive or dangerous weather. There's nothing to install or maintain. Our Weather Ops solution bridges information and timing gaps by providing the same critical information regardless of geographical location to key personnel using different methods of delivery such as email, text messaging, or mobile device push. There's no more coming back to the table to discuss the differing bits of information everyone receives separately, then create a plan. Our team taps you on the shoulder well in advance. And when we do alert you, your key team members receive the same alerts that allows you to instantly put plans into action. This will directly impact your bottom line in a very positive way. We're your weather team, and together we'll determine what works best for your organization, utilizing best practices to ensure your action plans are the best they can be, to protect both your physical and human assets. Daily forecast planners are created by our team that allows for easy identification of the types of threats that will impact you. You don't need to spend a half a day reading through multiple sources of weather information. By adding WDT to your team means efficiency, which leads to saving, to use for other areas to grow your business, or to make your events bigger and better. Our team provides preemptive taps on the shoulder. The hazardous weather outlook is issued daily by our team and is an in-depth analysis of potential hazardous weather that could affect your business or event. Key forecast drivers and forecast justifications, probability-driven assessments of each key weather parameter, and regional discussions can be sent as needed or required during periods of hazardous or inclement weather. Our weather check, like the daily planner, is referenced, color-coded for easy identification of threat periods that gets you ahead of making critical weather decisions. Threats that were identified in advance using that daily planner are now broken down in the weather check as the event draws closer. The weather checks are useful for timing guidance by identifying key weather hazard periods over the next 2 days in 2-hour time blocks. When dangerous weather strikes, timing is everything, and so are storm advisories and alerts are short-fused, event-driven alerts. These alerts provide you with details on exact timing and threat type. There's over 20 different categories, but for instance, severe storms, tornadoes, heavy rains, and high winds. Weather Ops will keep your team informed and connected, no matter where you are. Combined with our mobile decision support companion, you have instant access to radar, daily planners, weather checks, and alerts. You can react faster with more reliable information that allows you to protect what matters. I hope you all feel more confident in understanding radar and how it works, and will use RadarScope more and more. If you currently use RadarScope to help your company prepare and react to weather threats, give me a call. Let us discover how Weather Ops can help you be the last to close and the first to open.
Welcome to Advanced Spotter Training. In this video, we will delve into the world of radar meteorology. Now, this will be a fairly general overview, but there are a lot of excellent resources online should you choose to go beyond this training. So how does radar work? Well, this will be a very simple example, but it will certainly suffice for now. The radar located on the left side of the screen sends out a signal or a pulse. The signal then propagates through the air until it encounters something called a scatterer. Now, scatterers can be any number of things, from smoke particles from nearby wildfires, to birds or bugs, to the standard rain and hail. In this case, we're looking at a thunderstorm, so the radar beam is encountering raindrops and or hail within this thunderstorm. Once the signal hits these particles, a portion of the emitted signal is sent back to the radar. The radar then retrieves this portion of the reflected signal and uses it to piece together a radar image. The stronger the return signal, the heavier the precipitation. This example shows a single radar elevation at a specific time, but radars are constantly scanning and retrieving over 360 degrees. Once the radar makes a full revolution, it will increase the angle at which it is scanning, giving a more three-dimensional radar depiction. Once the radar has made several revolutions at several angles, something called a radar volume is complete. This will be important in the next slide, so remember it, radar volume. We begin with reflectivity. This is the radar parameter that you're probably most familiar with. Reflectivity, as stated before, is a depiction of precipitation. Colors range from light blue or green to a dark red or purple. Of course, this can vary depending on which source the data is coming from, as color tables can be easily changed. There are also two basic types of reflectivity, base and composite. Radar works by sending out signals at varying elevations. Assuming there's something out there to reflect that signal, a portion of the original signal will be sent back to the radar, as we saw in the illustration before. Larger and/or more closely spaced precipitation particles will reflect more of that energy back to the radar, giving them a higher reflectivity. Base reflectivity, as seen on the left side of the screen, is taken at a single elevation. Composite reflectivity, on the other hand, is a conglomerate of all radar elevations. Remember, we call this a radar volume, or a volume scan, in which the greatest reflectivity for a specific location, or radar bin, is displayed. The two images here show how base and composite reflectivity vary, as both images are from the same radar at the same time. You may notice base reflectivity provides greater detail and is higher in spatial resolution. Composite reflectivity tends to be a bit more blocky and may hide important low-level features, though both can be beneficial. This image, which comes from the Oklahoma Climate Survey, shows a zoomed view of one of the storms on the last slide. This is the historic Moore, Oklahoma supercell of May 3, 1999. Note the base reflectivity image and how it compares to the composite image. The base image from Tilt 1 shows a much higher resolution depiction of the supercell with a very clear hook echo. The composite image does not show this, but it does indicate the presence of an intense hail core and the likely presence of severe hail. When looking at low-level features iconic to supercells, composite reflectivity is almost worthless, but it does provide some idea of storm severity. We now move on to the second important radar attribute, velocity. Reflectivity gives us an idea of where storms are located and whether they contain light, moderate, or heavy rain and/or hail. But reflectivity does not tell us anything about damaging wind potential or whether the storm is rotating. For this, we must use velocity. Velocity is determined by the movement of precipitation particles within thunderstorms. Two primary colors are used to depict velocity, green and red. Green indicates that precipitation particles are moving toward the radar, or that winds are blowing toward the radar. Conversely, red indicates winds moving away from the radar. This gets a bit tricky because the radar is a point, and the way that the radar beam sweeps out in a circle can make certain velocity signatures difficult to discern based on where the storm is located with respect to the radar. Just like reflectivity, there are two main types of velocity, base velocity and storm relative velocity. Base velocity is simply the wind speed and direction with respect to the ground. Storm relative, as you may have already guessed, is wind speed and direction taking into account the movement of the thunderstorm. In the two images above, we are looking at a radar couplet, which indicates rotation. The base velocity shows some weak low-level rotation, indicative of a mesocyclone, but perhaps not a tornado. However, if we take the storm's forward motion into account, the velocity couplet becomes much more impressive, and a tornado vortex signature becomes obvious. We're throwing around a lot of complicated terms here, but you will become more familiar with them as we move through the presentation. Just remember that base velocity is ground relative, and storm relative motion, or SRM, is storm relative. Here we see an image showing the difference in base and storm relative velocities for the same storm. The image in the upper left portion of the screen is base velocity, and shows what appears to be a very weak circulation. We see two shades of red with the radar located southwest of the storm. It's important to know where the radar is located to get an accurate idea of what's happening within the storm. Reds indicate winds moving away from the radar, which would be to the northeast. The brighter the red shading, the stronger those winds are. So we see strong outbound velocities adjacent to weaker outbound velocities. It may take some imagining here, but that means there is some sort of circulation within the storm. In this case, it's a cyclonic or counterclockwise circulation. But because we are looking at ground relative winds, as this storm appears to be moving quite fast, the circulation is somewhat masked. Now, compare this image to the storm relative velocity image in the upper right corner of the image. Here we see a large area of outbound velocities adjacent to inbound velocities. Note the red and green colors adjacent to each other. This is a much clearer depiction of the mesocyclone and gives some idea of how strong the circulation is. On big, severe weather days when tornadoes are possible, we use storm relative velocity much more frequently than standard velocity. though base velocity can be very useful on days when damaging winds are more likely. Alright, now that we've covered our bases on radar reflectivity and velocity, we can delve into what some of this data looks like under varying conditions. Here we see the three main storm types as depicted in radar reflectivity. The most basic type of thunderstorm is called the pulse storm. The reason it's described this way is because these storms tend to develop and collapse quickly, pulsing up and down. The second type of storm, which requires more organization than pulse storms, are multi-cell storms. These are not individual storms, but rather storm systems made up of multiple smaller storms. Squall lines and mesoscale convective systems would fit into this category of thunderstorm type. The final and most severe storm type is the supercell. This will be the main focus of this training, though we will touch briefly on the other storm types before moving on to supercells. You can quickly see differences between these storm types, and there are really only a handful of environmental factors that affect what kinds of storms will develop on a given day. Wind shear and instability are the big ones. We will discuss this more toward the end of this lesson. As we mentioned before, pulse storms collapse almost as quickly as they go up. These storms form when there is little to no environmental wind shear, but adequate instability and moisture. Notice the reflectivity image on left shows some fairly high radar returns with the orange and red colors. Some pulse storms may contain hail, but there is rarely ever rotation with these storms. In fact, the greatest threat from pulse storms is damaging wind gusts. The image at right shows two divergent velocity signatures, areas where inbound velocities in green are closer to the radar than outbound velocities in red. We call this a downburst or microburst signature. These signatures don't always indicate severe winds, but given the right conditions, as pulse storms collapse, they may produce damaging winds. Pulse storms are common in Oklahoma and Texas, especially during the mid to late summer months. And it's not uncommon for the worst pulse storms to create 70 to 80 mile per hour wind gusts as they collapse. Contrary to pulse storms, multi-cell storms or storm complexes require at least some wind shear to develop. As individual storms collapse, they produce what's called outflow. With successive thunderstorm development collapse, thunderstorm outflows merge, creating what's called a cold pool. The outflow acts as a front, creating additional storms, and as these storms collapse, the cold pool and outflow are strengthened. Multi-cell storms often produce sporadic severe weather, including wind damage and large hail. On the extreme end of the multi-cell spectrum are derechos. Derechos are essentially squall lines that produce widespread, significant wind damage. These systems often contain bow echoes or areas of enhanced severe winds within the greater complex. The diagrams here show the evolution of a multi-scale convective system, or MCS. The complex begins as a single cell or cluster of closely spaced cells. As outflows from these storms merge, new storms develop, and a cold pool develops. Storm complexes often take on a comma shape over time, as illustrated here. Sometimes individual storms within multi-cell storm complexes can produce tornadoes. However, they are normally brief and fairly weak. In this slide, we see two examples of mesoscale convective systems as they would appear on radar. The animation at left is a reflectivity loop, which shows a comma-shaped area of storms extending from Broken Bow to Mullen, Nebraska. On the backside of this line of storms is an area known as the stratiform precipitation region. This area is actually where something called a rear inflow jet develops. The rear inflow jet is what ultimately keeps the storm system going and also produces severe winds at the storm's leading edge. Now, we won't go into this feature in too much detail, but it is worth looking up if you find some extra time. The image on the right shows both reflectivity and velocity for a fairly compact severe storm complex. This could be referred to as a bow echo, though many bow echoes are smaller than this one. Reflectivity shows an arc of heavy precipitation and hail oriented southwest to northeast. At the same time, the velocity image shows an area of inbound winds along the leading edge of the heaviest storms. These winds are in the 60 to 70 mile per hour range, so some wind damage is likely with this storm cluster. Note that we are referring to base velocity, not storm relative velocity, because we're more concerned with damaging straight line winds than tornadoes. final storm type, and the one that we will devote most of our time to in this training, is the supercell. We start here with an overhead schematic of a supercell. And we can easily match this diagram to an actual radar image from a supercell in central Oklahoma. Now, we've already used this image in previous trainings as well as in this one, so it should look familiar by now. This is an ideal example of what a supercell looks like in reflectivity. Many are not this well defined, and that's why it pays to have a basic understanding of radar reflectivity and velocity signatures, because it's not always going to look this clear-cut. There are many clear differences between this reflectivity presentation and the ones we've recently seen with pulse storms and multicell storms. For one, we see a clearly defined hook echo on the south and west parts of the storm. We'll discuss a bit more on how these develop in just a few minutes. We also notice a large rain-free area arcing into this hook echo. This is called the inflow notch, or inflow region of the storm. There's very little precip in this area because it's where the strongest updraft is located. So all of the precipitation particles, including large hail, are being lofted upward and suspended above the radar beam. Moving on to the most prominent feature, the precipitation area, we note that most of the precip is located to the north and east of the main updraft. This is very typical of classic tornadic supercells. Environmental wind shear acts to loft precip particles down shear, which in this case is to the north and east. This ensures that precipitation and associated rain-cooled air do not fall into the thunderstorm updraft. If this were to happen, the storm would lose its source of inflow and would be cut off, causing it to weaken and ultimately die. Because the heaviest precipitation is located away from the updraft region, the supercell is able to last for hours and hours and travel many miles without weakening. Finally, in extreme cases such as this one, a reflectivity ball or debris ball may be noted at the end of the hook echo. In this image, the ball of high reflectivity was associated with tornado debris being lofted far into the sky. The radar detects the debris just as it would any other precip particles. And because tornado debris is often much larger and more closely spaced than rain or hail, it generates a higher reflectivity. Now, these will not always be apparent, even in tornado-producing supercells. Related to the thunderstorm updraft is an area known as the weak echo region, or WER. This area is coincident with the inflow notch and the area of most intense thunderstorm updraft. Because vertical winds are so strong here, precipitation particles are lofted far into the atmosphere, resulting in an area of little to no reflectivity adjacent to the hook echo. This is seen in the lower elevation scans of the radar. As we ascend in elevation, more of these precipitation particles become apparent, and in the most intense supercells, a bounded weak echo region, or BWER, may be present. The BWER is an area of weak or no reflectivity surrounded by high reflectivity as seen in the image at right. It resembles a donut. If observing a storm with a BWER, be very careful that you stay well away from the precipitation core. BWERs indicate extreme vertical motions, enough to suspend very large hail particles such as baseballs and softballs. BWERs also indicate a greater likelihood of tornado development. Here we see a vertical cross-section through a BWER. Note that this supercell does not have the same classic hook look as the initial example we saw. A small but noticeable weak echo region is present on the southwest side of the storm, and as we look in the vertical, we see high reflectivity suspended above the area of weak reflectivity. This indicates a very strong updraft, and large hail is likely with this storm. Now we will discuss hook echoes more in depth. Here we have two examples of well-defined hook echoes. The image at left is from the standard radar that Weather Service offices around the country use during severe weather. The image at right is a high-resolution image from a Doppler on wheels mobile radar. Hook echoes are sickle-shaped protrusions of precipitation that form due to the low-level rotation pattern within the supercell. Rear flank downdrafts are instrumental in forcing precipitation around the mesocyclone in a counterclockwise fashion. This is what creates the appendage that juts out into the inflow region. On right-moving supercells, hook echoes are normally located on the southwest side of the storm, while left-moving supercells display hook echoes on the northwest side. We will go into more detail on right and left-moving storms in a few moments. Notice the high-resolution image contains a small donut hole within the hook itself. This is actually a tornadic signature. The high reflectivity surrounding the tornado is likely a mixture of precipitation and small debris particles. Notice that the tornado is located on the north side of the hook echo, as this is where the low-level rotation is maximized. Just because there's a hook does not mean there's a tornado. There are many supercells that produce substantial hooks that never produce tornadoes, though damaging winds and large hail are almost a certainty within the RFD. So now that you have a better understanding of hook echoes and reflectivity, let's look at an example using velocity. The radar images above are from the May 24, 2011 Central Oklahoma tornado outbreak. The two hook echoes circled were indeed associated with tornadoes. Note the balls of heavy reflectivity. These are actually debris balls associated with two violent tornadoes that occurred near Chickasha and Goldsby. Analyzing the velocity image at left, notice the location of the radar to the northeast of the storms. This means that inbound winds will be from the southwest and outbound winds will be from the northeast. And what type of velocity are we assessing here? You guessed it, storm relative velocity, because we're interested in low-level circulations and tornado potential. In each of these hook echoes, we have extremely strong inbounds adjacent to moderate outbounds. These are not only low-level mesocyclone signatures, but are what is termed a tornado vortex signature, or TVS. More on those later. Being able to quickly look at a radar image such as this and point out the most important features is critical in storm spotting. It will not only make you a better spotter, but also a safer one. We've already touched on this briefly, but a mesocyclone is essentially a rotating thunderstorm updraft. To detect mesocyclones, we refer to velocity data, typically storm relative, though mesocyclones can be detected through standard base velocity as well, just not as clearly. Here we see two examples of mesocyclones. The example at right would be classified a relatively weak mesocyclone. Note the inbound and outbound velocities aren't all that strong. This storm is definitely severe, but tornado potential is assumed to be relatively low unless visible confirmation is obtained. The example at left, however, depicts an intense mesocyclone and tornado vortex signature, though we haven't gotten to that just yet. Not only is it likely that a tornado is ongoing with this signature, but the tornado is probably strong to violent based on the extreme velocities we're observing here. Within the spectrum of mesocyclone size, strength, and longevity lie the mesovortices. These are very small-scale, transient circulations that are normally associated with squall lines or thunderstorm clusters. While these can occasionally produce very brief tornadoes, substantial swaths of significant wind damage are much more common. Alright, so let's look at a real-world example. This radar image should look pretty familiar to you. It's the velocity image we saw about 2 slides back on mesocyclone strength. When velocities are this strong, we actually have a new classification known as the tornado vortex signature, which I've already mentioned a couple of times. In order for this signature to be present, the velocity difference across two adjacent velocity pixels, or radar bins as we call them, must be at least 90 knots or around 103 miles per hour. In this example, we have inbound velocities of 80 knots adjacent to outbound velocities of roughly the same speed. This means our velocity difference, or gate-to-gate shear, in this small area is approximately 150 to 160 knots, or 170 to 185 miles per hour. For context, we have a photo of the tornado that occurred with this signature. You may recall the Greensburg, Kansas tornado of May 4th, 2007, which wiped out about 90 to 95% of Greensburg, Kansas, and was rated an EF5 on the enhanced Fujita scale. Outside of mesocyclones and supercell structures, there are other velocity signatures worth noting. These two are convergent and divergent signatures. Convergence is simply winds coming together, often indicating locations of fronts or boundaries, or strengthening thunderstorms. Divergence is just the opposite, and sometimes indicates a collapsing storm and potential for wind damage. Sometimes these signatures are mistaken for mesocyclones, and that's why it's very important to know exactly where the radar is located with respect to the area of interest, as this can result in misidentification. We're now going to move on to more dynamic processes with supercells rather than just simple radar signatures. However, understanding these dynamics is important in deciphering radar trends in supercell evolution, especially if you're out there spotting. The images above show a hypothetical three-dimensional rendering of a supercell thunderstorm. On the left side of both images, a representation of wind with respect to the storm is displayed. Note how winds increase with height, indicating what we call wind shear. This shear creates a horizontally rotating tube of air, sometimes called a vortex tube. As the storm develops, its updraft tilts the tube in the vertical. This forms a vortex pair, one rotating clockwise and one rotating counterclockwise. Assuming wind direction does not change that much with height, both of these circulations will intensify. A downdraft will then develop between the two, leading to a separation of thunderstorm updrafts. We call these splitting supercells. In the northern hemisphere, severe weather conditions normally favor the counterclockwise circulation, which is referred to as the right-moving storm. The clockwise rotating supercell is termed the left-moving storm. We'll see why here in the next few slides. We plot the wind changes with height on something called a hodograph. While the formation of the hodograph really isn't all that important for spotting purposes, it is important to know the three main types of hodographs that favor supercells and what you can expect to happen when storms begin to develop. When wind speed increases with height but there's little change in wind direction, we call this a straight line hodograph. This type of pattern favors mirror image splitting supercells. One glance at the time series above shows how one cell splits into two through time. One cell moves to the north, the left split, and the other moves to the south or east, a right split. The right-moving storm, however, persists and often lasts many hours. When winds both increase and veer, or shift from south or southeast to west or southwest with height, we call this hodograph clockwise curved. You can see by the clockwise shaped arc in the hodograph in the upper left part of the image. This type of wind pattern favors the right-moving supercell. This kind of wind shear is what we normally see on the big severe weather and tornado outbreak days. Notice that left splits tend to weaken rapidly once they move away from the dominant southern storm. Finally, we come to the very rare, especially in the northern hemisphere, counterclockwise curved hodograph. In this case, we would have north or northwest winds at the surface and west winds in the mid and upper atmosphere. As you can see in the image, this type of wind pattern favors the left splitting storm, and the right split rapidly dies as the storm moves east. This is much more common in the southern hemisphere with large tornado outbreaks there. Here we see a real-world example of splitting supercells. We have the dominant right-moving supercell in the center of the screen. Note the large, heavy reflectivity core and the broad hook echo with this storm. However, to the north of this storm is a smaller supercell that split off the dominant storm to the south. The arrows indicate the storm motion, so clearly based on the intensity of the main storm, we can expect some rather large hail with this storm. And we can see from the pictures that there was indeed some very large hail with the right-moving storm. So exactly what kind of hazards present themselves with these splitting storms? Well, the right-moving supercell is normally the one that's going to produce more significant severe weather, including tornadoes. The left split may, on rare occasion, produce tornadoes, but it's normally known more for very large to extreme hail. Splitting storms and storm mergers are a real challenge for storm spotters and safe positioning. The white arrows indicate storm direction. Note the cell in the lower left portion of the image. This storm will likely merge with the storm in the center of the image at a later point in time. The X's on the screen represent varying storm spotter positions. If you're positioned at the pink X, the left split is headed your way and you can bet on some very large hail. At the white X, you may be on a more interesting storm, but because you're looking into the precipitation core, you're not going to be able to see the interest area of the storm. The red X marks the best location to observe the most intense area of the dominant supercell. But caution should be stressed here, because these storms often take hard right turns and may move toward this location, especially as low-level rotation is increasing prior to tornado formation. Another consideration is that the storm at the bottom left of the screen may merge with the storm in the center of the screen, so it may close on your position if you're at the red X. So just to recap, remaining well to the south and east of the hook echo and inflow area is the best place to observe supercells for rotation and tornado formation. Make sure you're paying attention to other storms around you, as there is rarely only one significant storm to worry about. With spotter positioning in mind, it's important to discuss outflow boundaries and their role in enhancing tornado potential. Outflow boundaries act as a source of low-level spin for supercells, and if these storms interact with the boundary in just the right way, they can become tornadic in a hurry. The image above illustrates how this process works. Initially, the boundary is removed from the thunderstorm. As the storm approaches the boundary, or the boundary drifts toward the storm, horizontal vorticity is lifted along and behind the boundary. This is then drawn into the storm, increasing its rotation. At the same time, cloud base is lowered because air along and just behind the boundary is normally cooler than the air ahead of it. This causes clouds to form at a lower elevation, ultimately lowering the cloud base. With lower cloud bases and stronger storm rotation, tornado potential increases. Storms can become tornadic in a hurry along boundaries, and it's critical to pay attention to them if you're out spotting. In this real-world example, a storm intersects with an outflow boundary in the upper left portion of the top image. We see a well-defined hook echo in reflectivity and a strong velocity couplet in the bottom image, indicating the presence of a tornado. Note the area of convergence along the boundary indicated by the long stretch of inbound and outbound velocities coming together. The last thing we will discuss as far as thunderstorm types are concerned are elevated thunderstorms. We actually just saw an example of these kinds of storms on the last slide. Elevated thunderstorms form above a layer of stable air where atmospheric instability resides. On the last slide, the area behind the outflow boundary was stable at the surface, but because there is still instability above the stable layer, the storms continue. These are called elevated storms because they do not draw their energy from the surface air mass. The image above shows an atmospheric sounding. The green line denotes atmospheric moisture, while the red line depicts the temperature. Now don't get too caught up on the details of the plot. It's very confusing. Just understand that the area below the steep temperature increase, called an inversion, is where the stable air mass is located. The air above this, however, is still unstable. Depending on the amount of instability, elevated thunderstorms can produce large hail, but storm rotation is not able to penetrate this stable layer near the ground, so they never produce tornadoes. We will finish up this lesson by discussing a relatively new radar technology known as dual-pole radar. Standard Doppler radar only scans in the horizontal. This is fine for most radar interpretation activities, but it only provides a two-dimensional aspect on precipitation. In order to obtain additional information, the radar must send out both horizontal and vertical pulses. This is known as dual polarization, or simply dual-pole radar. Because we are scanning in two directions, we can now discern three-dimensional properties of precipitation particles. Since this is still somewhat new, we're still looking at ways to incorporate this data into our radar interpretation skills, but we figured we'd at least give you a taste. For now, we'll just focus on one simple example of what dual polarization data look like. Here we have a 4-panel layout for a tornado-producing supercell. We're going to focus in on something called the tornado debris signature. The idea of the TDS is simple. The radar detects tornado debris as it's being wafted inside the tornado through a parameter called correlation coefficient, or CC. CC is a way of measuring the similarity of precipitation particles within a storm. If the CC value is close to 1, the particles are very similar in size and shape. But when CC values fall below 0.7, the particles are very dissimilar. Rain and snow will have high CC values because they're usually very similar in size and shape. But tornado debris can vary wildly in shape and size. The example above shows both reflectivity and velocity in the upper two panels. Reflectivity contains a large hook echo, and velocity indicates a strong rotation signature co-located with this feature. Don't worry about ZDR in the lower left, but do pay attention to the circle-shaped area of very low correlation coefficient in the bottom right portion of the image. This is the radar sensing debris within the tornado itself and indicates that the tornado is ongoing and has caused some kind of damage as debris is present. Take note, debris signatures that last for a long time likely indicate the presence of a strong or violent tornado. Storms with a persistent TDS or several TDSs should be given extra room to breathe, as erratic storm movements may quickly put you in a dangerous position. Here's another example from the tornado that struck Moore, Oklahoma on May 20th, 2013. Note the high reflectivity in the upper left and very strong couplet in the upper right portion of the image. In the bottom left panel, correlation coefficient shows a circular area of very low values associated with debris being lofted by the tornado as it moves east of Newcastle. After looking at several radar scans in the vertical, it was noted that this tornado lofted debris up to around 4 miles above the ground. The bottom right panel shows the final tornado path from the ground survey, which confirmed the tornado was among the strongest on the enhanced Vegeta scale, an EF5. Alright, now that we've trudged through all of the technical stuff and all of the different radar parameters, we're going to go through a quick radar simulation to sum everything up. This will touch on pretty much everything we've learned in this module. Many of you may recall the incredibly wide tornado that struck rural areas between El Reno and Union City, Oklahoma on May 31st, 2013. In this series of images, we will only look at the half-degree reflectivity and storm relative velocity images from around 6 p.m. to 6:45 p.m. Central Daylight Time. We turn first to the reflectivity image on the right. Note the area of very high reflectivity north of I-40 and west of El Reno. This likely indicates an area of hail. And we also see this drops off dramatically to the south in an arc-shaped fashion. If we were to observe reflectivity at higher elevation scans, we would see a clear weak echo region and bounded weak echo region in this area, consistent with supercell structure. We would expect very strong inflow in this area, and turning to velocity at left, we see this is indeed the case. In fact, the inflow at this level is so strong, the radar has interpreted it to be an inbound signal, moving out of the storm, and we know this is not logical. This is a velocity artifact that sometimes occurs with obscenely strong velocities. Looking more closely at the velocity image, we do see a somewhat weak but tight circulation developing. A brief tornado had been reported just a few minutes prior to this scan, and if a tornado had still been ongoing, this is exactly where it would have been. 5 minutes later, we have a much more impressive signature, both in reflectivity and velocity. Notice the hook echo forming on the southwest side of the storm, just to the south of that reflectivity gradient we spoke of earlier. This indicates a rapid organization of the storm. Now turning to velocity, we have a clear TVS with impressive inbounds and outbounds right next to each other. We also see the persistent area of inflow to the east of the tornado. This should tell us that this supercell has a strong source of fuel and energy and is not likely to weaken anytime soon. And given the moist, unstable air moving into the storm, it may produce more than just this one tornado. And as if you hadn't already guessed, this is where the tornado would have been located. As we move through time, we continue to see this very impressive reflectivity and velocity structure. The velocities actually become quite complex at times because this tornado is so large and contains multiple smaller circulations within the parent tornado, a multiple vortex tornado, or multivortex. Finally, the tornado reaches I-40 and becomes nearly stationary. Note the TVS sitting right on the interstate between El Reno and Yukon. Turning to reflectivity, it is apparent that the tornado is completely rain-wrapped. Nothing in the reflectivity image alone would tell you a tornado is present. This is why velocity is so critical in the warning process and in safe storm spotting. This is a classic example of a storm that should prompt you to keep your distance. Erratic changes in speed and direction of the tornado resulted in several fatalities as people were struck by the tornado in their vehicles on the rural roads south of El Reno. The velocity couplet finally weakens at around 6:42 p.m. Central Daylight Time, though other weak circulations persist well into the evening. We also see several other storms developing back to the west, and these storms continued into the overnight hours, producing flash flooding in many locations. We'll finish with an animation from the historic May 20th, 2013 tornado that struck Moore, Oklahoma. In this animation, we'll only look at reflectivity, but rest assured the velocities were just as impressive. Notice the long arcing hook that wraps into the high reflectivity ball just southwest of Moore. These high reflectivities are due to a very high concentration of tornado debris being sensed by the radar. Often these are referred to as debris balls, and we've seen a couple examples of these in earlier slides. As the animation plays, one can see the individual reflectivity elements spiraling into this area where the tornado resides. The tornado dissipates to the northeast of Moore, but as debris continues to fall from the sky, we see an area of high reflectivity where the tornado has lifted. Well, that brings us to the end of our presentation on radar interpretation. Thanks for your attention. Hopefully you're more equipped to understand what you see on radar, ultimately keeping you and others around you safer while storm spotting. The next section of the Advanced Spotter training will focus on where to find information for basic severe weather forecasting.
Traveling through the air, hitting that mountain over there, and traveling back to me. And the time it takes between you shouting hello and when your ears hear is determined by the distance between you and whatever your voice is bouncing off of. Okay, sounds pretty simple, right? Hello! Hear that? That's the sound of my voice traveling through the air, hitting that mountain over there, and traveling back to me. And the time it takes between you shouting hello and when your ears hear is determined by the distance between you and whatever your voice is bouncing off of. Okay, sounds pretty simple, right? Well, that's exactly how echo radars work. This episode of Test Tube 101 is brought to you by the United States Air Force. An echo radar emits a sound wave and then waits for the echo to come back to its receiver. By timing the returning echo, you can work out exactly where another object is. And when using multiple receivers position... Hello! Hear that? That's the sound of my voice traveling through the air, hitting that mountain over there, and traveling back to me. And the time it takes between you shouting hello and when your ears hear is determined by the distance between you and whatever your voice is bouncing off of. Okay, sounds pretty simple, right? Well, that's exactly how echo radars work. This episode of Test Tube 101 is brought to you by the United States Air Force. An echo radar emits a sound wave and then waits for the echo to come back to its receiver. By timing the returning echo, you can work out exactly where another object is. And when using multiple receivers positioned at different angles, it can determine...
Welcome to Skywarn, severe weather training from NOAA's National Weather Service in Bismarck, North Dakota. I'm John Paul Martin, your warning coordination meteorologist. In this segment, we'll talk about... Welcome to Skywarn, severe weather training from NOAA's National Weather Service in Bismarck, North Dakota. I'm John Paul Martin, your warning coordination meteorologist. In this segment, we'll talk about Doppler radar. Doppler radar... Welcome to Skywarn, severe weather training from NOAA's National Weather Service in Bismarck, North Dakota. I'm John Paul Martin, your warning coordination meteorologist. In this segment, we'll talk about Doppler radar. Doppler radar is a very important part of the National Weather Service warning decision-making process. Here's a picture of the Doppler radar outside of your National Weather Service office in Bismarck. Doppler radar sends energy out, and it listens. Sends energy out, and it listens. On the right-hand side is inside the radome, the Doppler radar dome. This dish is 32 feet in diameter. It goes around in a circle, sending energy out and listening. Once it completes one revolution, it stops, shifts up a little bit, and goes around again. Again, sending energy and listening. Stops, shifts up a little bit more, goes around again. So that we're taking slices of the atmosphere. The energy from the radar goes out in a horizontal pulse and then a vertical pulse. This way, we can get a better idea of the size and shape of the object that was hit, and then determine if it was a raindrop, snowflake, hailstone, or dirt or smoke in the air. This is called dual pole or dual polarization, vertical and horizontal. There are different modes we operate the radar in. There's clear air mode, where on a sunny day or a day with no precipitation, the radar scans only the lowest levels of the atmosphere. During precipitation or thunderstorms, the radar is in what's called a precipitation mode, and we scan more layers of the atmosphere to give us a better idea of the extent in the vertical of the precipitation or the thunderstorm. There are a few radar limitations. The first is the cone of silence right over the radar. As a thunderstorm moves over the radar does not sample the whole thunderstorm anymore. It can't see the whole thunderstorm, so it may appear weaker. As the storm comes out the other side of the radar sees the entire storm again, and it may appear as if the thunderstorm grew stronger, even though through the cycle it did not increase or decrease in intensity. Another limitation of the radar is that the Earth is curved, and so the farther the energy goes away from the radar, the higher up the energy is in the sky. So at greater distances from the radar, the energy is at higher levels in the atmosphere. There are some gaps in radar coverage. It does not mean along the Montana-North Dakota border. It does not mean that there's no radar coverage. It means it's limited from the surface of the ground up to about 10,000 feet. The coverage is more limited, again, the farther you go away from the radar. Here's a drawing, a schematic of a supercell thunderstorm. Every thunderstorm has air that moves up, we call that the updraft, and air that moves down, we call the downdraft. Under the updraft, any precipitation here is being lifted up into the thunderstorm. It's falling out here, under the forward flank downdraft. Again, under the updraft, the motion is upward into the storm, so very little or no precipitation falling there. Rain and hail falling here under the downdraft. There's another area of sinking air in a supercell thunderstorm called the rear flank downdraft. This is what grabs the circulation out of a thunderstorm, the rotation out of a thunderstorm, and brings it down to the ground in the form of a tornado. So keep that diagram in mind as we look at this thunderstorm over Grant County, North Dakota. Again, the energy sent from the radar was sent out. The energy hit something, energy came back to the radar, and it painted a picture. Here's the scale from on the bottom of the screen, from light blues all the way up through the purples and white. This is called base reflectivity, a reflectivity image. The energy reflected off of objects and came back to the radar. Small raindrops return a little bit of energy to the radar. The radar paints them blue and green. Large hailstones, especially large wet hailstones, return a lot of energy to the radar. The radar shows those on the high end of the scale in the dark reds, the purples, and the whites. So this base reflectivity depicts the intensity of precipitation from energy return, shows precipitation, boundaries, and non-weather targets like smoke. Most of the time, this is what you see when you look online for radar or on television. They show the base reflectivity of the lowest slice from the radar. This image is off the Bismarck radar and depicts smoke from a grass fire. The wind is from the northwest, and so the smoke from the fire near Cannonball on the Standing Rock Nation is going to the southeast, across Emmons County and into South Dakota. Again, this Doppler radar is so powerful, it can detect smoke and dirt and dust particles in the air. Another image we get off the radar is base velocity. This is showing us how fast things are moving in the wind, and we can infer from that the wind speed. If the radar determines the object is moving toward the radar, it's painted green, and if it's determined it's moving away from the radar, it's painted red. Again, green is toward the radar and red away, and so this day we have a northeast wind over the radar site. The wind is coming from the northeast and going to the southwest. Another important display off the radar is the storm relative velocity. This compensates for storm movement and makes it easier to see the wind pattern in and around a thunderstorm. In this radar image, we see the radar is off to the right of the image. It's the Minot Air Force Base radar located near Deering, North Dakota. The radar sent energy out, Energy hit something, energy came back to the radar. The radar determined the motion here was away from the radar and here was toward the radar. You can see this broad circulation away and toward the radar. If we look closer, you can see that we have these reds right next to the greens and blues. This is tight rotation, tight circulation inside the thunderstorm. This is actually a tornado. If you were near Bow Bells, North Dakota this day, you saw this large tornado. This is what you saw with your eyes, and in this image is what the Doppler radar shows. The National Weather Service, outlined in yellow here on the radar screen, had a severe thunderstorm warning for this storm, and outlined in red, the red polygon here, was a tornado warning on this storm. Again, base reflectivity and storm relative velocity can be used together to get a better idea of the storm structure in a thunderstorm. Here's our forward flank downdraft where precipitation is falling. Here's our updraft area where you see a weak area in the radar returns. Again, the updraft area. And back here is our rear flank downdraft, pulling circulation out of a thunderstorm and down to the ground. And indeed, there is a tornado in this image near Joplin, Missouri. Again, the radar is off on the right of the screen. The red is motion away from the radar. The greens and blues towards the radar. You can see this large circulation with the thunderstorm. And if we zoom in, you can see this rotation, very tight rotation. Again, away from the radar, toward the radar, right next to each other. This was a tornado near Joplin, Missouri. Again, the radar has limitations. Storms that develop on top of the radar or move over the radar may appear weaker or to weaken, when in reality they may not be weakening. Showers off in the distance that are small, the radar energy may go over the top and not even know the shower is there. The radar may not detect that rain shower. Terrain is also an issue with radar. As the energy swings around this side, most of the energy will go into this mountain and come back to the radar, and it'll paint a picture, the radar will paint a picture of the mountain and may not see, may not detect the rain shower beyond the mountain chain. But those limitations, there are a few, and they do limit the radar. But the benefits of Doppler radar far outweigh these few limitations. I want to thank you for watching, and I ask you to stay weather ready.
Welcome to White Horse Radar's demonstration video presentation.
Welcome to Skywarn, severe weather training from NOAA's National Weather Service in Bismarck, North Dakota.
With the basic size of an object that the sound waves have bounced off of. But if we add an additional layer, we move into Doppler radars. Doppler radars emit a radio wave too, but also keep track of the radio wave's phase. Hello! Hear that? That's the sound of my voice phase. Basically, its shape, position, and form. When the radio wave returns, it's measured again to check for any changes in its phase. If the frequency
Doppler effect and its applications. Have you ever heard a police car, ambulance or fire engine pass and heard the siren change suddenly? Based on many observations, an Australian physicist and mathematician, J.C. Doppler, proposed the Doppler effect in 1842. According to him, the Doppler effect is the shift in frequency and wavelength of waves which emitted from a source moving with respect to the medium a receiver moving respect to the medium, or even a moving medium. In this image, we have a ball. Let's pretend it's a fire engine. The fire engine is about to start sounding its siren in a minute. We can see the sound waves propagating towards from the source. This is the sound wave created by the siren. As you can see, it travels in all directions equally. As a result, any observer on any side of the fire engine would hear the exact same sound, because the wavelength and frequency is the same in all directions, as the sound waves are coming from a stationary source. The wavelength is the distance from the crest of one wave to the crest of the next. It can also be true to true. The frequency of a wave is the amount of waves that pass a given point in 1 second. In the case of this video, it is about one wave every 2 seconds. In order to understand the Doppler effect, let's see how wavelength, frequency and pitch are related. We already know that the frequency of the waves in this video are about 1 every 2 seconds. But watch what happens to the wavelength when the frequency of the waves is increased to 4 every 2 seconds. Speed the siren up by 2. So, if you double the frequency of a wave, you halve its wavelength. Next up is the relationship between frequency and pitch. It's quite simple. All it says is that the higher the frequency of a wave, the higher the pitch will be. High frequency is equal to high pitch and low frequency is equal to low pitch. So, the relationship between all three is high frequency equals short wavelength equals high pitch. Low frequency equals long wavelength equals low pitch. Now, we can understand the Doppler effect. The Doppler effect explains what happens when the object that is creating the sound begins to move. This time, we will watch the sound waves with the siren muted. As you can see, the sound waves are bouncing up towards the front of the moving object. They are also growing further apart at the back of the moving object. This means there is an apparent change in the frequency and wavelength of the waves at the front of the object. There is also an apparent lowering of the frequency and wavelength of the waves at the back of the object. The object is still producing the same amount of sound waves, but its motion is making the frequencies and wavelengths to change at the front and back of the object. So, what would
He came back shifted next.
I'm sure you've probably heard the term Doppler before, but did you know the principles that we use in our weather radar today was developed more than 150 years ago by an Austrian physicist named Christian Doppler? He found that the occurrence produced by a moving source of waves in which there's an obvious shift upward in the frequency for observers towards whom the source is approaching, and an obvious shift downward in the frequency for people for whom the source is moving away. Okay, let's simplify the Doppler effect for you. Think of a car on a road honking its horn. While the car is traveling towards you, you can hear the high-pitched sound of the horn. But suddenly, after it passes by, the pitch lowers and drops. Now, this is a perfect example of the Doppler effect, and this is how it's used in weather radar. The radar sends out a pulse of energy, which then reflects off an object, such as a raindrop. Now, some of the energy reflects away into the air, but the majority of it goes back to the radar, where it then calculates how far away the raindrop is, how intense the rain is, and which way the raindrop is moving in relation to the fixed radar site. Now that is where the Doppler effect comes in. We use the data sent from the most powerful radar in East Tennessee at the National Weather Service office in Morristown to our Storm Tracker 6 computer to show you the rain, sleet, and snow. But during severe weather situations, the wind speed and direction is what is the most important. If the wind in a small space is going away from the radar in one area and towards the radar right next to it, this can show that there's rotation within the storm. And that means there's a possibility